ডাইরেক্টলি একদম স্টার্টিং থেকে স্টার্ট করা হচ্ছে। চ্যাপ্টারের নাম, দ্য টপিক নেম ইজ দ্য সলিড স্টেট, সাবজেক্ট কেমিস্ট্রি, ক্লাস 12, সেমিস্টার 2। সলিড স্টেট টুডে কী করা হয়েছে? আই ডিড দ্য ডিফেক্টস। ফার্স্ট ইজ দ্য stoichiometric defects, and secondly are the non-stoichiometric defects. No, first is the point defects. In the point defects there are stoichiometric defects, impurity defects, and lastly we have the non-stoichiometric defects. In the stoichiometric defects, the ratio of the cation is to anion or the overall composition of the compound is always maintained, and whereas in the non-stoichiometric defects the cation is to anion ratio is interchanged. I can say that the overall composition, or there is a word, I forgot the word. No, I forgot the word. The overall composition is changed. I will search for the word, okay, at the end. So in the stoichiometric defects we have vacancy defect, we have what was that, একটা হচ্ছে vacant থাকে, means there are vacancies, and another interstitial defect means some extra is added. So in case of the vacant defects, the density is decreased because vacancy is created, so the density is decreased. In the interstitial defects, the vacancy, I mean extra atoms are introduced in the interstitial sites in between the atoms already in arrangement. In the interstitial sites extra atoms are being introduced, so automatically the overall density of the solid increases. Now comes the Frenkel defect. It is a combination of the vacancy defect and the interstitial defect. So one atom is displaced from its original position and it enters into the interstitial site. It occupies its neighboring interstitial sites. So here what is happening, it is again I say it is a combination of vacant defect and interstitial defect. So the density is interchanged, is not interchanged, it remains the same. And it is also known as the dislocation effect. It is also known as the dislocation defect. It is because an atom is being dislocated from one position into the interstitial site. Now you see, as there is no introduction of new extra atoms, or there is a withdrawal, there is not at all withdrawal of any atoms already in arrangement in the crystal lattice, so the overall composition of the compound also remains the same. At last we see the Schottky effect. Schottky defect, not effect, it is defect. Schottky defect. In case of Schottky defect, we see again the cation is to anion ratios are same. One thing I forgot about Frenkel defect, that it is caused usually in the ionic solids, and mainly in case of the ionic solids in which the cation size is lesser than the anion size and the density is not changed and remains the same in case of Frenkel defect. Now we come into the Schottky defect. In the Schottky defect, the cation and anion remains ratio remains the same. Number of cations is to number of anions remains the same. It means the overall composition remains the same. The net electrical charge remains equal throughout the defect. before the defect and after the defect, the net electrical charge remains the same. So there is no difference, it is neutral as always. So how this defect occurs? যতগুলো অ্যানায়ন ভ্যাকেন্ট হয়ে যায় ততগুলো এই ক্যাটায়ন ভ্যাকেন্ট হয়ে যায়। ইট ইজ আ টাইপ, ইউ ক্যান সে ইট ইজ আ টাইপ অফ ভ্যাকেন্সি ডিফেক্ট। বাট এখানে নেট ইলেকট্রিক্যাল চার্জ রিজার্ভড থাকে, সেম থাকে, নিউট্রাল থাকে বিফোর অ্যান্ড আফটার দ্য ডিফেক্ট। ইট ইজ বিকজ যতগুলো ক্যাটায়ন উইথড্রল করা হয় ভ্যাকেন্ট হয়ে যায়, ততগুলোই অ্যানায়ন উইথড্রল করা হয় বা হচ্ছে ভ্যাকেন্ট হয়ে যায়। সো দ্য নেট electrical charge remains the same. Now then comes the other defects. I don't actually remember all those exactly, but non-stoichiometric defect comes, and within the point defects also comes impurity defect. In the impurity defect we see metal excess defect and metal deficiency defect, maybe, but I'm not quite sure right now. One thing from this chapter, various numerical problems come from those areas of edge length and FCC, BCC lattice, 14 Bravais lattices. One important thing to notice that from the 14 different Bravais lattices, there are only 4 BCC lattices. So it is a fact, it is a knowledge, I think so. It is a fact that we have to remember that, we have to memorize that shit. And then except this, what we have nothing. We have the numerical problems from edge length. The relation between the radius of each sphere or each atom and the edge length, which is denoted by a, small a. Now from here we have to make 2 columns. On the left side we write element or slash atom for an element or for an atom. It means the sphere part, in the corners, in the face, in the body center, whatever. In the sphere part we write all about the sphere or the atom or the element on the left side, and on the right side we write about the unit cell. What comes within the unit cell? Within the unit cell we can get edge length, which is denoted by a, and then it comes the density, rho equals to the mass of number of atoms per unit cell, it is divided by a cube, means the volume of the cube. Now we can calculate the number of atoms per unit cell, like there is a table. If you remember that, like for FCC, for first of all we have the simple cubic, which is also known as the primitive one. Secondly we have the BCC lattice. Thirdly we have the FCC lattice. Fourthly we have the end centered cubic lattice, ECC lattice. So for all these 4 structures we have the number of atoms per unit cell, also denoted by capital Z or just simply Z. Now here we can automatically we can on the spot we can derive the equation on the spot, like during the exam, so we don't have to worry about that. And on this side, on the left side, we previously had the atom part or the sphere part or the element part. Under that part we have the atomic mass part and the Avogadro number. How is atomic mass represented? XAMU, atomic mass unit or just unit, XU or XAMU. What is X? X grams is the weight of Avogadro number of atoms of that element. So what is the weight? Atomic mass is the weight in grams of 6.023 into 10 to the power 23 number of atoms of that element. So it is known as the atomic weight or AMU, atomic mass unit. The unit is AMU or U, atomic mass unit. Now from this side we will take the Z value from the right side, and we will take this Avogadro number, and we can get an easy relation between the density, volume, mass. We have this side, and on this side we have that Avogadro number relation. We can just join and we can get the required result as directed, as needed, as required. So that is it, and elsewhere everything is finished. We have to read the lattices and the tables very correctly. And one thing is left here, which is the semiconductor part, the N type, the P type. I was solving MCQ problems and I just noticed that, I just realized that if we just remember that N type means the group which is containing nitrogen at its very first element in the group. So the group which is starting with nitrogen, also known as the group 15, also called the nitrogens, is known as the N-type semiconductors. Like those elements of group 15 are mixed as doped as dopants in the mixture of any other compound. Maybe in order to increase the conductivity, electrical conductivity. I'm not sure about that. And and the other type of the semiconductor, which is the P-type semiconductor, here group 13 elements are mixed as the dopants in the compound, as dopants or as impurity. So what is dopants? It represents impurity. So dopant is just impurity. Now N type means nitrogens starting with nitrogen, the group starting with nitrogen, which is group 15, and here on the other side the P type, which is group 13, BAlGaInti, boron, aluminium, gallium, indium, and thallium. And in the N type we have nitrogen, phosphorus, arsenic, antimony, and bismuth. This was the group 15 one, and I think we are just done. We did it. Like this was all the MCQs, and in between, there were some numericals, 1 or 2 or 3 maybe, which were quite impossible to just solve. So I left it alone, and I am okay with how much I had done. Just done. Okay.